Well, now, have you ever had a bad experience on a flight, like an emergency in there? You've had a couple of those. We had an aborted takeoff one time. That was exciting. I was in Atlanta. We were, we had to be, we had to be like 1 second from wheels off the ground. And all of a sudden, they just powered it way down, and the front of the plane came down, and they pulled off into the grass. And they said that we had a light come on. So I mean, we're sitting in the grass while other planes are taking off. It seemed like way off the books. So then the pilot comes over, and this is in a big plane. The pilot comes over and says, "Okay, we're going to try this again." Pulls back in line, and we're barreling down the runway again, and pretty much the exact same point where we're about to take off. All of a sudden, somebody, I assume it was one of the cabin stewards, or maybe it was a co-pilot, I don't know, came screaming over the intercom, cell phones off, like in a panic. Like, I assume that they were having some light come on that related to like radio interference or something, but they still took off. It was a couple minutes. Things were a little. There was another time we were landing. I think this was in Arizona. We were landing in the fog, and it seemed like we had been descending for like ever, but you couldn't see anything outside. And then all of a sudden, we got under the fog light, and we are like on top of houses. And we are nowhere near the airport. And the pilot just guns the engine, just pulls straight up. I mean, it was pretty. I'm guessing the instruments weren't working as well or something because of the fog, or you didn't have great visual. That was exciting. Yeah, I feel like we probably would have survived that one. I mean, I think we were only a couple hundred feet off the ground. I mean, we were almost hitting houses. It was pretty awesome. Love that. Yeah, my wife, she had never flown before we had met, and she learned fairly early. Because she said she used to look at me to see, you know, if I was like with turbulence and stuff, if I seemed nervous, then she knew something was wrong. But then she realized that's not a good, because I like extreme turbulence. Like, I want to hear like the wings creaking. So good. I also like on cruise ships when they hit rogue waves. They got the barf bags out. Oh, it's great. I just love that stuff. So now she looks at the cabin crew if they're panicking. I am on medication, by the way. So this is being treated. This is treated. This is the treated version of this. All right. So you're saying you don't like extreme turbulence? Like concerned you're going to fall out of the sky type turbulence?
I haven't experienced that.
It's so good. Especially when you're flying overseas and it happens when everybody's asleep, like at 4 a.m. And, you know, they're cruising at like 80,000 feet. And all of a sudden the whole plane just starts like jostling all the place, and the lights start flickering. Oh, so good. All right, so we were supposed to write, do some toasting, right, for illegal moves, count the number of moves, and toast when we win. All right, so let's finish this guy up and then move on to the shunting yard algorithm. That's a strange. What happened? Have you heard that sound before? It was a screenshot. Yeah, no, because that's a different sound when I start that. Yes, that's still good. Huh? So I started. That's recording. Yeah. Yeah. We gotta. I mean, something really hilarious might come out, and you might want to share that in the dorms.
Yeah, exactly.
Is that what they call them? Res halls now, not dorms?
You know, the res life people are not allowed to call them dorms.
Why?
Because I don't know exactly why, but
Is dorms like a derogatory term or something? Really? Huh. I wonder what the deal is. No, I mean, I'm guessing if they're not allowed to call them that, there's probably a derogatory connection there.
Because it's more than just living in the dorm. It's like all of residence life and everything that goes on around campus.
Oh, so it might not actually be derogatory. It might just be bad branding, potentially. Makes sense. Okay, so right now I can pop, and if I push back, that's illegal move. But if I pop, push here, pop, and I try to push to that center column, it's not letting me. We want to get some error messages for that, do some toasting. So let's make that guy work first. So we'll go into our main activity here. All right, and here's our try to push. So right in here, when we try to push, if we get into an else where we actually don't push, this is where we'll go ahead and do our toast. So what was it? Toast.make text. And is this guy takes what? The context. And then the message, illegal move. And then toast.length short .show. So that'll show some toast when we push illegally. All right, so there's no such thing as, well, actually, I suppose we could pop illegally if there was nothing there, right? So here's our try to pop. We'll just still have it say illegal move. That's good enough. All right, so let's test that for our illegal moves. All right, so we'll try to pop from here. That's the empty stack. Here's the empty stack, so we get an illegal move for that. We'll pop from here. We'll push there. I clicked a bunch of times, so let's wait for that guy to finally go away. There we go. I like that. I tapped a bunch. All right, so now we'll try to make a legitimate illegal move with a push. So that was the illegal move, but I can move here now. All right, so that seems to work. Okay, so now we want to have a counter that tells us the number of moves we've had, and we're only going to count that if something either pushed or popped. Well, actually, we want to do this only on a successful pop or a successful push, because we now have the ability to have an unsuccessful pop, I guess. So we need a place to put this, so we'll go in here, and here's this horizontal linear layout, but all of this is inside of a vertical linear layout. So I am going to I guess I can put it right before this, but under the buttons. Well, whatever. But so that would be below my placeholder. All right, so I'm going to go ahead and we'll put it right there. So I'm going to have a text view. And we'll center that guy. Use gravity. Am I on the wrong thing? Oh, I am on the wrong thing. That's why it wasn't showing me what I wanted it to show me. Oh, it didn't actually drop in because this is my placeholder view group with the text view in it. Well, hold on, that's weird. Oh yeah, because I add the button to that guy when I pop it. So that guy's supposed to be empty. I wanted to add my text view here. All right, that looks better. All right, so we're going to call this guy count. Count TV. And since he's a text view, we should have why is it putting it inside of a linear layout? Or why is it selecting that? This guy is going to be called count TV. And this guy is going to have the text centered. All right, and we'll start this guy off saying count is 0. All right, then each time that the count goes up, we need to update that guy. So we're going to go ahead and give ourselves programmatic access to count TV. So I'll give myself a private text view count TV. Inside of here, we'll say this dot count TV is equal to the text view version of this dot find view by ID r dot ID dot count TV. All right. Then we're also going to have a private int count, and we'll start count off at 0. And we already have the thing saying count colon space 0 for our default thing. But now every single time we successfully pop, we want to update count. So I'm going to give myself a private void update count function. And what update count will do is it'll say this dot count plus plus, so we'll increment count, and it'll say this dot count TV dot set text to count colon plus this dot count. All right, so that'll be update count. So then when we successfully do a pop, we'll say this dot update count. When we successfully do a push, we'll say this dot update count. Like that. So now we should have our count going up whenever we actually are able to make a move. Go ahead.
Is there a good reason why concatenating and using string literals in set text produces some error? That it wants you to use string variables as a value?
So you saying I'm going to get an error here?
No.
You're talking about the warning.
Error, I meant warning.
Because they want you to use, there's this file called strings.h in resources. I think it's under values. Or strings.xml. So inside here, you can create a string. And it's considered to be higher performance if you use the created string as your resource in there. But since we're building a concatenated thing, they might say use the string value from this guy, and then use whatever value you're going to concatenate onto it. I've never used it. I probably used it before, but I don't use it very often. Sometimes I'll use it for colors if we're doing a theme for the app, but never for strings. I really feel like it's something that's left over from a long time ago, and it probably does have some sort of performance benefit when you're using the same string over and over and over again. And probably the real advantage is if you want to change it, you change it in this one place. and then it changes throughout the application. But in this case, we're only saying count in one place, so it seems like that's a reasonable thing. All right, so we'll do a pop, count goes to 1. We'll do a push, count goes to 2. We'll do a pop, count goes to 3. We'll do a push, nothing happens, count doesn't move. Now, if we push it right back to the same place, that's technically a move, so there's count is 4, so on and so forth. All right, so count seems to be updating the way it should be updating. All right. Now, the reality is, if we are counting the way that Towers of Hanoi would actually count, when I pop and then push, that's actually considered a single move. That makes sense? So with that in mind, if we wanted to make it work that way, we would not update the count inside of pop. And that would give us an accurate count based on what like the online Towers of Hanoi thing. We do count when we push, though. All right, so notice count has not gone up. Push, pop, push, pop, push, pop, push. Yep, so that's the best score you can get for that is a count of 7. Okay, but now we want to know, because right now I can still pop and push and do all sorts of stuff to break my win, right? And now it's still going up. So we need to know when we've actually won. So how can we detect that we've won? Okay, so we can use a Boolean to keep track of whether we've won, but how would we detect? How do I know that we're in the winning state?
If you go through the list, then each disk should get successively larger in this implementation. So, if this dot cur disk dot get next disk is larger than this dot cur disk dot get size or whatever.
It seems extremely overcomplicated. Because we already have a whole bunch of rules in here that only allow disks to get into a certain position, right? So we're in a winning position when the number of disks in tower 2 or tower 3, whatever I name the last one, is equal to 3. Right? There's 3 disks in the far right tower. We won. Is that accurate? So we need our towers to now know how many disks they have in them. So we'll have a tower keep track. We'll say private. Oh, yeah, that's for the tower visual. We can ask the tower visual for its count. We can do that. Let's keep track of the count as well, but it'll give us the same number. I'll show you what he's talking about here in a second. So we're going to say private count, private int count. And when this guy's first created, we'll say this dot count is equal to 0. There's nothing in a tower when it's first created. As we push a disk onto the tower, we allow the disks to go on here. Now we're actually, we know that whenever push gets called, because the way we've written this, we've done the policing of whether something's allowed to go onto this tower external to the tower. So we know that we're only going to ever call push when it's allowed. That makes sense? Where we will have a successful push. So we can always say this dot count plus plus there. Similarly, when we pop, we're going to remove the disk to remove, but only if it was not equal to null did we actually reduce the number of disks that were on the tower. So inside of this if statement, we'll say this dot count minus minus. Then we'll go ahead and give ourselves a getter. So we'll generate a getter for count. And now after each move, because we do have towers at bucket 2 is our tower where winning would occur, right? So after each push, so try to push to the tower. If a push actually occurred, we'll ask the question, if this dot towers, well, actually, if we want to put this in its own function, even though it can only happen here, let's just do that. We'll create a function and call it. So we'll say private void check for winner. And this guy will ask if this dot towers at bucket 2, that's our far right tower, dot get count is equal to 3. That means we have a winner. So we'll go ahead and do a toast dot make text this winner toast dot length short dot show. And then what we want to do on top of this is we want to keep them from making future moves. All right, so let's just test this for right now. So after we successfully do a push, we're going to go ahead and say this dot check for winner. And this should at least give us a toast when we do have a winner, when the third tower has 3 elements in it. So we'll go and run this. So there's our toast for winner. All right, but the problem right now is I can still pop stuff off and just keep on trucking. All right, so we probably want to go ahead and keep ourselves from making future moves. So we'll go ahead and add a Boolean. Private Boolean is winner. We'll start this guy off at false. And then we'll only let pops work when winner is false. So that means when we check for winner, wherever I wrote that, if we have a winner, we'll say this dot is winner is equal to true. We now have a winner. And then when we pop, so try to pop. Here's our try to pop. We're only going to check any of this stuff if, well, we can actually just do it right here. We can do if temp is not equal to null and this dot is winner is equal to false. So not this dot is winner. So if there isn't a winner and we have something to pop, we'll allow them to pop. As soon as winner gets flagged as true, no more popping. That makes sense? And you can technically put these in either order, but probably the more efficient way of doing it would be to put the is winner thing first and go ahead and let that fail before we check for anything else, but it's probably about the same. So let's check this again and make sure that after we have a winner, we can't move anymore. All right, so there's our winner. Row. Oh, it's interesting. So I updated my screen. So if this is not equal to null, so let's just try to pop. Oh, because I actually do pop. I physically do pop there. I just didn't update the, okay. Yeah, so we really need to wrap because of the way we've written this. We need to only do any of this if this dot is winner. I'm going to actually just do a return. So this is technically that guy. So this will just bail out of this function if there's a winner, rather than wrapping all this stuff inside of an if statement. All right, so, and typically this would have been written, and most programmers would probably write that like that, rather than putting the curly braces. You can remember back to 200, I mentioned that curly braces are never wrong. You know, you're always okay putting curly braces because technically if statements and loops only have one statement following them. In this case, the shorthand version of this would certainly be, if there's currently a winner, go ahead and return. And return says, make this method immediately end. I'm not returning any individual value because this guy is void. That makes sense? If you don't like that trick, you can then say, if there's not a winner, then we can do all this stuff. If that makes you happier. It'll operate the exact same way. Only if there's not a winner will I even try to do any of this. All right, so we have a winner. No more popping. Make sense? Okay. So does that pretty much solve the homework assignment? Maybe the only other thing you'd want to do maybe is give a reset button or something like that to go back and play the easy version of Towers of Hanoi again. But we'll just leave it at this and move on with life. Okay. So I'm going to go ahead and stop this. And let's commit. Okay, so now, because we're moving towards being able to do the shunting yard algorithm, we're first going to need to create a queue. So let me go ahead and close this project. We'll start a new Android Studio project. And we're going to call this guy shunting yard. We'll say CSC300 underscore spring 2018 underscore shunting yard. All right, go ahead and hit next. Empty activity. Okay, so while that's loading here, let's go and look at the shunting yard algorithm to make sure we understand it. All right, so the idea of shunting yard is you should be able to take an input, I think they give you an actual number-based one down here. No, they don't, that's fine. So, assuming A, B, C, and D are all numbers in this case. Is that making it any bigger? Is that visible? We can see it well enough? All right, so you have your input. So we're going to read something in as a string. So maybe it's 123 plus 5 times 2 minus 8, something like that. All right, now we're going to have to break that string up into individual tokens, individual nodes that are going to be stored on our various data structures. All right, so we'll look at that here in a second, but assuming we have these individual nodes. So here's a number, here's an operator, here's a number, here's an operator, here's a number, here's an operator, here's a number. Those all get put onto our input queue. And now the difference between a queue and a stack. Can I have Keynote open? So we said that a stack is a last in, first out data structure. A queue is a first in, first out. Queue is a first in, first out data structure. All right, so we can think of that this as being like a traditional line. At McDonald's. You get there first, you're going to be the first one to get served. That type of thing. All right, so queues have two functions typically. We have NQ, that is, get in the back of the line, or add end, if we want to think about it like that. And then we have DQ, which is the ice cream place. So DQ says remove from the front of the line, or remove front. Okay, so those are the only two functions that queues have. NQ and DQ. Get in the back of the line, get removed from the front of the line. Make sense? All right, so we're going to go ahead and write a queue. We're going to use our same node data structure we've used up to this point. So guys, just going to have a payload. Now, in this case, we might decide we want our payload. So let's be a little bit more object-oriented in this case. We actually have two different kinds of nodes, right? We have in our world here, we have nodes that hold numbers, and we have nodes that hold operators. Make sense? All right, so we're going to be more object-oriented about this. So what I actually want to have is I want to have a linked data structure, because we're going to have queues and we're going to have stacks here for holding this stuff for the shunting yard. But they're all going to be capable of holding the same kinds of nodes. But now I want nodes to come in two flavors. I want nodes that hold payloads that are integers, and I want nodes that hold payloads that are chars for operators. Okay? How would you implement the inheritance model for this? If we decide we're going to have a node setup, we have a class called node, and then from there we have something called an op node, and then something called a num node. How would you implement this? Go ahead. Okay. All right. Are we ever going to actually create an instance of a generic node? Or in our world here, are we always going to have op nodes or num nodes? So if we want to create a class that we don't actually intend to create an instance of, what do? Make it an abstract class. All right, so we're going to create an abstract class called node. Create a new Java class. We're going to make this guy called node, and we're going to click the little button there for abstract. So we'll make that guy an abstract node, or you can just create it normally and change it to abstract, whatever makes you happy. All right, so here's my abstract class node. Now, nodes all have a next node, correct? So I'm going to say node next node. So they all get one of those, correct? So that next node will be something that is a node. All right, so leave our abstract class like that for a moment. In fact, we can go ahead, actually, let's do this. We're going to say public node, and this guy will set this dot next node equal to null. Because initially, when a node is created, the next node will always be null. Right? Okay. But I've made this guy abstract, which says we cannot create an instance of node. So we ask the question, okay, well then who's going to call this constructor? The answer is its children. Okay, so now let's go and create an op node. So we're going to create a new Java class. We'll call this guy op node. He's not going to be abstract. Now we're going to say op node extends node. So he's going to be a child of our node class. And op nodes have a private, and actually let me, well, I'll come back up there in a second. These guys have a private char payload. Now, in our node class, we probably want to make next node be protected. Protected says it's accessible inside of node as well as inside of children of node. So we'll make that guy protected. All right, so there's a little invisible next node in here. And then because we got that through the inheritance model. And then we're going to say that op nodes actually have a char-based payload. We'll go ahead and create our constructor for op node. So public op node is going to take in a char payload. And we'll say this dot payload is equal to payload. But we want to go ahead and leverage our parent's constructor for setting the next node equal to null. And if we want to use our parent's constructor, it has to be the very first thing we do in here. So we're going to say super. This will call the parent's constructor. All right, so we're calling upon our parent's constructor. Our parent is node. We look at node, the constructor takes no parameters, so I am passing it no parameters. And that guy will do the work of creating my initial object and setting the next node variable to null. Make sense? All right, so that's going to be our op node for right now. Now, we're going to go ahead and we're going to create another node called num node. Oop. New Java class, num node. This guy will extend node. He's going to have a private int payload. And we'll have a public constructor for num node. And this guy will take in an int payload. We'll go ahead and call our parent constructor to set up the next node. And again, next node is a generic node. And we have two different kinds of generic node, well, two different things that are nodes in our world right here. We have num nodes, which is a node, and then we have an op node, which is a node. So either of those guys is considered to be a node. That makes sense? They're specialized versions of nodes, but they are nodes. So next node can point to either a num node or to an op node. And we'll say this dot payload is equal to payload. All right, and we have that guy. Okay, so now we have our num node and we have our op nodes. If we want to get the next node, we can go ahead and implement that inside of node. So inside of node here, I'm going to go ahead, I'm going to create, I'll generate a getter for next node. Now we can make this guy public or we can make it protected. Probably want to make it public depending on where our logic's going to be. So whether I'm dealing with a node or I'm dealing, well, we'll never actually be dealing with a generic node. We'll always either be dealing with an op node or a num node. But both op nodes and num nodes will inherit the getNextNode function, which will give you access to the next node variable, which is of type node. And that node may be an op node or it might be a num node. So we're going to have some way of identifying the two of them. And I'll show you how to do that. All right, that makes sense? Okay, so we'll go ahead and inherit that method to all the children of the node class. So op node has everything you see here, but he also has a next node, and he has a function called get next node. Num node has everything you see here, but he also has a next node, and he also has a function called get next node. All right, now we also probably want to write a set next node, because as we're piecing apart our things that are coming in, we need to be able to set that next node. So we're going to say, well, where we use the generate again. Generate, setter, set next node. Okay. We're not going to be able to write get payload here. One thing you could do to police this is you can say that all classes that inherit from this have to write an abstract get payload. But the problem with that is payloads come in multiple flavors. We have an int-based payload, and we also have a char-based payload. So because of that, we really can't say they have to write a get payload. We'll have to write them over on the other side. But you're not overriding the same thing. Because there's two get payload, one's going to return an int and one's going to return a char. So I can't write it here because then the other guy will only override one of them. Right? They have different versions of get payload. So I can't really police it here, which is fine. So we'll just have to remember as programmers that these two dudes need to be able to advertise their payload properly. If we would have made our payload an object type here and then hidden within it the type of thing it was, we could have written it more generically. But let's just leave it like this. You could make it work that way, but then you'd get the Unicode value of it when it came out. So I think that might be more secretive. Like you might expect it to work one way, but you're getting all these weird Unicode values out of the get payload for your op node. This is a small little function, and it'll generate it for us. So we'll just use this guy. We're already being more object-oriented than we typically are. So inside of op node, we'll create a getter for payload, and that guy's going to return a char. Inside of num node, we'll create a getter for payload, and that guy's going to return an int. All right, so now we have the ability to get the payloads, and we have the ability to get and set our next nodes. And that's something we inherited from our parent node. Make sense? All right, so if we want to draw the picture of this real quick, nodes come with a next node variable. They also come with a get next node function. And a set next node function. So this node, which is abstract, so we'll make that in red. That guy's abstract. We cannot create an instance of him. He houses these things. All right. These guys are children of that guy. We can create instances of those. And these guys have a op node have a char payload. Num node has an int payload. And then they both have a get. get payload function that will return the respective payloads. That makes sense? So we've written the generic node stuff one time at the top, but we've made this class abstract, which means we cannot create an instance of it. Then we went ahead and inherited from those two guys, from that one guy, these two objects, and we gave them the ability to store different kinds of payloads. One stores a char, one stores an int, and then gave them the appropriate get payload from those that will return the right kind of value. Okay, so makes sense the model we've created here? So we've created an inheritance model where we didn't need to duplicate this logic twice. Okay, so now we're going to go ahead and build our queue and build our stack. So we're going to create a new Java class stack. Well, let's build a queue first since that's new. We've already built the stack before. So we'll build our queue. Okay, so queues are going to have an enqueue and a dequeue. So it'll be beneficial for us to keep track of the front and the end of the list for easily adding things, right? So we're going to go ahead and create a private node front, a private node end. Then the constructor for queue, public queue, we'll set this dot front is equal to null. There's nothing in the line. This dot end is equal to null. All right, and now we need to write enqueue and dequeue. So public void enqueue will take in a, we actually need two versions of enqueue. One that's going to take in a char and one that's going to take in an int, depending on whether we're enqueuing a operator or a number. So this guy will be a char C. So we'll call it payload. So he's going to take in a char payload. And because he's a char payload, we're going to create a op node to add him to the end of the list. So we're going to say op node on is equal to a new op node, and we'll pass this the payload. So that will create an op node for us. And we want to add this op node to the end of our list, which means that we want to set op node dot set next node equal to whatever this dot end currently points to. And then we want to say this dot end points to op node dot set next node. I'm sorry, to just op node. All right, so go ahead.
Well, I don't want to lose your train of thought, but I'm like confused with what are we trying to accomplish?
We're building a queue with.
How does that have to do with what you were doing on the website?
I was doing over here.
No, on the website.
Oh, for shunting yard?
Yeah.
Yeah, we haven't talked about the shunting yard yet, but this guy is a queue. Yeah, we're going to need a queue here. We're going to need a stack here, and we're going to need a queue here.
And we're just setting it up.
We're giving ourselves the building blocks that we're going to need to solve this problem. So we're kind of running out to Home Depot and getting all the tools that we're going to need to actually implement this guy.
What is an op node and a num node?
Op nodes will hold operators, like a plus sign. Num nodes will hold numbers like 17 or 28, that kind of stuff. Okay, so enqueue, we're going to say we'll create the new op node if we're building one out of a char. We're going to set his op node equal to this dot end. And then we'll say this dot end now points to this new end of the list. Now, we do want to be careful if we are adding something to the empty list. So if we said after this, if we said if this dot front is equal to null, then we'll say this dot front is equal to this dot end. So if we were coming in and we were adding something to the empty list, we can call it a queue all we want, but it's just a specialized list. If head and tail, or front and end, both point nowhere, and I created this brand new guy that I want to add to the end of this, I'm definitely going to make end point to that guy. He's definitely the new end of the list. But if front currently points nowhere, we're going to have him point to that guy too. But only if he currently pointed nowhere. Because if he actually pointed somewhere, now we have at least a two list where end points to the end of the list and front points to the front of the list. All right, but when somebody first walks into McDonald's and nobody's at the counter, the front of the line is the same as the end of the line. That make sense? Okay. So that's in queue. This is get in line is what this guy is. So here's the guy we're going to get in line. And actually, I'm going to write this a little bit more generically just for the sake of object-orientedness here. So I'm going to say private void enqueue. This guy's going to take a node n as a parameter. I'm going to steal that stuff. We'll put it in here. So whatever kind of node we have, either an op node or a num node, we will set that node's next node to end, set end to point at that guy. Then, if front currently pointed nowhere, we'll make front also point at that new guy. So this guy will enqueue any kind of node. So then our enqueue versions here, we'll just call this dot enqueue, passing it our op node, and then we'll have a second version of this function. That takes an int as a parameter, creates a num node, we'll call that NN, and then we'll pass that num node, which is a node, into our enqueue for node. So we write the structural function enqueue that takes a node as a parameter and knows how to add any kind of node to the end of the queue. And then we have two public functions. This guy's private, so he's only usable inside of this queue class. Then we'll have two public functions that will be called externally from this that will either be passed a char or an int, and they'll create the correct kind of node for that, and then use our internal enqueue method to add that node to our queue. Does that make sense? So we're getting more object-oriented than we historically have. All right, because now we have this data structure that is holding a couple of different kinds of nodes. And rather than building two different queues, I kind of need them to live together. So I need my data structure to hold a generic-y thing called a node, but then I'm going to have two different kinds of nodes that'll slip in there because they're still generic nodes at their core. All right. So that's going to be our enqueue, that's going to be our enqueue, and this is going to be our enqueue. What's it called when we have multiple functions with the same name but a different number and or type of parameters? Starts with a P. Ends in an ism. Has an ollie in it. Polymorphism. Polymorphism. Remember that word now? All right. Polymorphism. More than one function that have identical names, but they take a different number and or type of parameters. Well, I am a doctor. So it's well, it actually isn't just a computer science term. It talks about having more than one thing with the same name. So that would apply in a lot of different things, but it is definitely used in computer science for this term. But there are other examples of polymorphism in nature. What's this? Well, I could have had two. I have two different answers to that. So I can say I am a doctor. Then the other one is I did stay in a Holiday Inn Express last night. Have you seen those commercials? Some of you have seen those commercials, right? There's all these Holiday Inn Express commercials that, like there'll be somebody out for a jog or something like that, and somebody falls down and breaks their ankle. And this guy will run up and try to help them. And it's like, oh, are you an orthopedic surgeon? He's like, no, but I did stay in a Holiday Inn Express last night, which is supposed to make you smarter or something like that, because it's a good hotel. That's their advertising. That's their marketing thing. So it's stupid, but you remember it, right? We've seen those commercials, haven't we? None of you? I wonder when the last year that commercial was on. It's kind of a scary, I don't want to look. It's got to be in the last 5 years. I think there's one in the last 5 years. They still reference those on TV shows. Just watch it, look it up. It's like 1994 was the last time that commercial was on. They've never actually made a high definition version of the commercial. It's always standard definition or black and white. It's pretty bad. All right, so that's going to be NQ. Now we need to write DQ. So DQ is going to just return a node for us. Now we could actually get a little fancy here if we want, but we might come back and do that later. I think I'm going to make it more generic here because I'm going to show you a way we can compare these things. All right, so NQ. Well, now we're going to write DQ. So we're going to say public. This guy's going to return a generic node. Now we're ultimately going to be returning either op nodes or num nodes. They're going to fly out of here as a generic node. And then somewhere else we'll have to ask what kind of node was this. Okay? So we'll say public node DQ. All right? And this guy needs to detach the front of the list. So we'll ask the generic question. We'll say if this dot front is equal to null. That means I currently have the empty list. I'm going to go ahead and just return this dot front. I have no disconnecting to do. Okay? Otherwise, I need to do some disconnecting. So what disconnecting am I going to do? I am going to have to give myself the node, call this node to return, and this will equal this dot front. Okay? If I'm in this else, I know that this dot front is a thing. It's a real thing. All right. Now, I'm going to change this dot front to be this dot front's next node. But before I do that, I want to know whether I was dealing with the one list. I want to know if this dot end is also equal to this dot front. All right. So if this dot end is equal to this dot front, they're both the same. Then the guy I'm removing here is the one guy that exists, and they're both just going to become null. So I'll say this dot front gets the value null. This dot end gets the value null. So I'll zero out the list then. Otherwise, if they're not the same thing, I had at least two elements in here. I will say this dot front dot set next node is equal to this dot front dot get next node. So I'll make the front of the list point to the second guy in the list. all right, which might be pointing now to the end of the list possibly, but they at least weren't the same. Because if they were the same, we had the one list, and now we just empty the list. They're both null again. I've reset them. All right, so if they were the same, empty the list. Otherwise, go ahead and update front to point to his own next node. So he now points to the second guy in the list because I'm going to return node to return. Return node to return. That is the front of the list. One way or another, that's the front of the list. Whether we had a 1 list or we had a 40 list, that's the front. And he's been disconnected because front pointed to this guy, and we updated front's next node to, let's see, front's next node. I'm actually lying here. We're going to make front equal front's next node. Because the new front of the list is going to be the second guy. So we'll make front equal his own next node. We're not setting front's next node to his own next node. That would be redundant. We're saying the new front of the list is the current front of the list's next node. All right. Then we'll go ahead and change node to returns next node to null just to fully disconnect it. So we'll say this dot, it's not this dot. Node to return dot set next node to null. That'll fully disconnect it from the list. And then we'll return node to return. Make sense? Okay. So that's DQ. DQ will always spit out a generic node. Okay, so now let's go into main activity here. And we're going to do, just show you a couple of interesting examples. I'm going to create a QQ is equal to new Q. All right, then we'll say Q dot NQ, and I'll go ahead and I'm going to pass this guy a 10. Q dot NQ, I'll pass this guy a plus sign. Q dot NQ, I'll pass this guy a 3. So this is as if my original string looked like 10 plus 3. Make sense? So I've added things to the end of the line. So this was the first guy. He was at the end of the line. Then the new end of the line is the plus. Then the new end of the line is the 3. Okay? Now, I'm going to go ahead and start dequeuing things. So these guys went in as generic nodes to our queue. So if I do a system.out.println q.dequeue, we're going to see what that pointer looks like. We know the first one should be a number. We know the second one should be a op. So one should be a num node, the other one should be an op node. Make sense? Because when I built a node with 10, that built a num node. When I built a node with a plus sign, that built an op node under the hood. So now when I dequeue those couple of guys, I'm not dequeuing the 3 yet. If you here, I'll just go ahead and dequeue the 3 as well for testing. So I should have a num node, an op node, and a num node. Let's go ahead and run this. Oh, I'm just going to need my logcat here. So there's my hello world. Let's see, where are my... All right, so there's my num node, the first guy that came out. But my dequeue appears to be broken. Or my NQ is broken. One moment. So this would be the case where I have the 3 things in there. So I'll grab the front. That should have been the 10. I'll ask if front and end are the same, which they're not. So I get into the else. I'll set the new front to be the old front's next node. And then I'll disconnect node to return from the rest of the list. And I'll return it. That looks accurate to me. So we need to look at our enqueue. So enqueue takes in a node as a parameter. And we'll go ahead and set that node. Set his next node to point to the current end. Fine. Then we'll make the current end point to that new node. Fine. Then we're going to ask if the front is currently equal to null, which means we had the empty list. Go ahead and connect it to this guy. I'm not printing it out here, but this doesn't seem right to me. Because front is only ever getting updated. No, end will be equal to an actual node here. Let's draw a picture here real quick. All right, so if I have a 1 here, and I have a 2 here, those couple of guys in line, and then I have a front and an end. Oh. All right, endpoints there. So initially, let's just have it like that. So we just added a node. So these guys both point to null. I create this new node. I make end point to him. Fine. So here's my new node. I make him point at whatever end points to. I set his next node to point to wherever end points to, which was null. So both these guys pointed out nowhere. So this guy points out nowhere now. Then I make end point to him. Then I ask if front is currently null, make front also point at end. So since this was the 1 list, front was pointing out nowhere. So now we also make him point here. So adding to the 1 list looks fine. Now, I bring in my next node. Next node gets created. I set his next node equal to, I set his, okay, this is where I'm breaking it. I need to set n's next node equal to n, to my new guy. This is where I'm breaking it. This should be this dot end. Because we're adding to the end of the line. We're enqueuing to the end. If this dot end is equal to null, we'll say this dot end is equal to n. That's it. Else, if this dot end is an actual thing, we'll say this dot end dot set next node to end, or to n rather, and then we'll say this dot end now equals end. So we'll make the current end point to the next guy, then we'll make the end point to the new end. Okay. Otherwise, if there was nothing at the end currently, we'll just make end point to that last guy. And then situationally, we'll make front point to this last guy as well. You probably could have compressed this down a little bit. So let me run this real quick. Make sure this is doing what it should be doing now. Yeah, so here's our num node, here's our op node, here's our num node. All right, now I'm going to show you one more thing real quick. Take 10 seconds because it'll help you in your homework assignment. I'm going to print out that guy, instance of num node. I'll print out this guy, instance of op node. And I'll print out this guy, instance of op node. We know that this guy's a num node, this guy's an op node, and this guy's a num node. Instance of is a Boolean operator that returns true if this guy is an instance of one of these. So I should get a true because this is a num node, so he is an instance of num node. I should get a true because this is an op node, so he's an instance of op node. I should then get a false because this is a num node, and I'm checking to see if he's an op node. All right, so this is a Boolean operator to check to see if something is one of these other guys. Let me just see my true, true, false real quick. And then here's my true, true, false. So your homework assignment is just the first part of shunting yard. It has nothing to do with shunting yard. You're going to read in something that'll look like 10 plus 3 minus 2, that kind of thing. And you're going to turn that into a queue of num nodes and op nodes. So you'll have a text box on your interface. You'll just type in a string that looks kind of like this. You'll hit one button, and that button will process that string, turning it into the different kinds of nodes that it should be. So you're going to have to parse this string, walk through it. Some hints, you might choose to use string tokenizer. That might be helpful. Or you can just walk through it character by character, whatever makes you happy. All right. And then all you have to do is turn it into a queue. If you want to visually show me the contents of that queue, you can. If you just want to write a display method for the queue, print it out to the screen, that's fine as well. Make sense? So you're not doing any of the math yet. You're just breaking the string up and building the queue in parts with our two different elements. We'll do the math stuff next class. Got it? All right. I will see everybody on Tuesday.